Thank you all for coming. So yeah, one of the big questions that I'm trying to answer is where the dark matter is in the Milky Way. And to do that, I'm using this thin, kind of very fragile looking streams of stars that are orbiting our galaxy. And to kind of set the stage, probably noticed there are papers recently or the news articles.
I can't hear you very well.
You have to speak up, yeah. No, it's not, you just have to speak up.
Okay, good. I'll hear like a few news articles that came out in the course of the last few weeks. And there's been a breakthrough in our precision with which the mass of the Milky Way galaxy. And it turned out that it's very massive. So when these people looked into the motions of stars in the Milky Way, they said that they saw that they're moving very fast. And this means that something needs to hold them together. And so they inferred that the mass of the galaxy is something like 1.5 trillion times the mass of the sun. So this is a lot. Because when we look into the galaxy and kind of estimate how much mass we see in the stars, it's something like 70 billion. So that's a lot. That's a lot of mass. But it's still only 5% of what these articles are telling us that the whole should be. And so if we have a cartoon picture of the Milky Way, we think it looks like this. So there is 5% of everything that's in it is in this stellar disk and a slight bulge at the center. Our sun is over here, slightly offset. And then there's this huge halo of unknown matter, or the dark matter. So the question is then obvious, like this is, and it's not just the Milky Way. We look at other galaxies. Everywhere we look into the universe, we see like only 5% and an indication that there is 95% missing. And so it's a big question because we would like to understand the universe and what it's made of. And there's been a lot of resources being dedicated to search for this dark matter. So we think it was detected gravitationally. It's pulling other stars, but we want to see if we can detect it in some other ways. So there have been big experiments dedicated to seeing if it interacts with ordinary matter. So here I'm showing a picture of an ex-gold mine in South Dakota, so very deep underground, that was repurposed into an experiment to search for dark matter. So you can see this giant cave over here as they were digging up. Now this is where a tank full of xenon is, and they're monitoring what is happening, hoping that if some dark matter particle passes through the tank and interacts with the xenon, that we might be able to detect this. But you can see that there's a question mark over there because this is all hypothesized. We haven't yet detected anything. It's coming up empty. There are other models of dark matter as well. So we think that if it doesn't interact with ordinary matter, maybe it interacts with itself and then annihilates. And so there is a space mission targeted at observing this through gamma rays that was launched more than a decade ago. And there are some kind of interesting signals, but nothing really panned out. So this also kind of came up empty. And then, of course, as you must have heard coming to these talks, there's these giant accelerators that can produce particles. And that would be the ultimate kind of way of understanding what dark matter is if we can actually produce it in the lab. And so a large part of what the LHC in CERN is doing, so this is a giant accelerator in the Swiss Alps, they're looking for dark matter if you can create it by colliding just ordinary matter together. And coming up empty. So you can see like the price tags over there. It's a not insignificant amount of money that is being dedicated. And this is all for the tests that we are not even sure that they will work. So the only thing we know for dark matter is that it interacts gravitationally. And then that's what makes it hard. But luckily, there's still some hope for understanding what it is, because depending on the type of particle dark matter is, it should be distributed differently in the galaxy. And so I'll just show here three different distributions, like three different models of dark matter and how they would be distributed around the Milky Way galaxy. So I'll start here with this cold dark matter or very massive dark matter. So this is in units where a proton is something like 1,000. So this would be like 1,000 times less massive than the proton would be the candidate dark matter. And if that's the case, there should be a lot of it in this galaxy. So the Milky Way would be just like a small part over here. And the basic prediction is that there should be a lot of these small clumps of dark matter that are orbiting around. So if we look at another model where the particle is 6 orders of magnitude, so 1,000,000 times less massive, a lot of this structure kind of goes away. So it still has same general shape, but very fewer of these clumps. So it's much smoother galaxy and much more stable in a sense. There's nothing like very much going on around it. And then we can go on the very, very low mass end. So this is, very low mass end. To this extent that the particle is so low mass that the quantum effects become important on macroscopic scales. So in this case, this prediction is that there should be no clumps at all orbiting the Milky Way. It should just be like some interference pattern. And so this is what we are trying to do. We know that dark matter interacts gravitationally with ordinary matter. And we have these different predictions of what the distribution of it should be. So my goal over the next few years is to create the highest resolution map of dark matter in the galaxy and then see if we can distinguish between these three scenarios. And really what it kind of hinges on is whether we can detect these small clumps and how many of them there are in the Milky Way. And so it turns out that the way we go about doing it, we start with something very familiar. So I have a question for you. Do you recognize what this is? Yeah? What does someone say?
The Galita Slough?
Yeah. Do you want to guess how it's connected to astronomy?
Tides out.
Exactly. So this is a tidal pull. And it turns out that tides will be a crucial element of everything I'll be talking today. And so just to understand a little bit of how tides work, we'll revisit them on the Earth. So we know that tides on the Earth are caused by the gravitational pull of the moon. So in the basic picture is that since moon is on the one side of the Earth, it is pulling like the gravitational force here on the side closest to the Earth is larger than the force at the center of the Earth on the force on the other side, on the opposite side of the Earth from the moon. And so if we go kind of look at from the perspective of the Earth, this would kind of look like that there is like some force pulling out Earth in one direction towards the moon and on this other direction away from the moon. And so the cartoon picture and turns out the solution of how this shape of the Earth, if we imagine it being completely squishable, becomes something like this. And this is kind of why we have the tides. And what we can then do is calculate, since we know the whole configuration, we know the mass of the moon, the mass of the Earth, and their relative distances, and we can calculate how strong the force of the moon is on the Earth. So this is, I promise, the only equation in this talk, but it is a fun kind of order of magnitude thing that I want you to appreciate as we go along. So what we'll be looking at is the ratio of this acceleration caused due to the tides with respect to the Earth's gravity. And so it turns out that this is like this big equation that really only depends on the ratios of the size of the Earth divided by the distance to the moon, and then the mass of the moon divided by the mass of the Earth. Do you know sort of order of magnitude, how big those are? Some, what?
1/6.
Close. A little bit bigger. Something like 60 to 1 and like 80 to 1. So Earth is 80 times more massive than the moon, and the moon is 60 times farther away from the Earth than the size of the Earth. And so it turns out when you kind of calculate those ratios, it turns out that this tidal acceleration or tidal force is 10 to the minus 5% of the force of the Earth. So it's a very minor effect. And, we see it, like the average difference in the height of the tides is something like 0.5 meter when you average over all of the planets. So, it's something we can see, but it's very minor. But it is useful to have this kind of number and this expression, because now, since we know how tides work on the Earth, we can just see how they are apply this to some other system in the universe. And the ones that I'm really most interested in is the question of star clusters in the Milky Way galaxy. So I said that the galaxy is made out of stars, but then it turns out that there are also some more coherent clumps of stars. So I drew them like in a very cartoon way over here. And so what we can then do is see how are the tides affecting these clusters. And to aid us, we'll just create the same cartoon as we did before. So here is, now instead of the Earth, we have the cluster. And instead of the moon, we have all of the Milky Way that's doing the pulling. So instead of the mass of the moon, we'll have the mass of the Milky Way that's inside. This distance will be the relative distance. And this will be, again, in capitals, the mass of the star cluster and the radius of the star cluster. And so now when we look at the ratios, we can see that they're like very different. So the size of the cluster is much smaller than its distance from the center of the Milky Way galaxy. So it's something like 5 times 10 to the minus 4. However, the Milky Way is much more massive than the moon. It's like this is 200 million times more massive than the typical cluster. And so you can see that, or you can guess that the tides will have a very different effect on the cluster than they have on the Earth. So another image for you. Do you know what is being shown in this picture? Pleiades. Yes. So over here we have Pleiades. Do you know another star cluster in this image? Hyades, exactly. So this is the kind of head of the Taurus, and this is a very much more loose group than the Pleiades. And so these are nearby groups of stars, and we can, since we know how far away they are from the center of the galaxy, and they're so close that we can count all of the stars and measure its mass, we can estimate what this tidal acceleration should be of these clusters. And when we apply our formula we had from before, it turns out it is not like in the Earth, 10 to the minus 5%. It is something like 5 or 1%. And so this is not a huge effect, but much bigger than what we had before. So I think that this actually might be doing something. And what turns out that it's happening is when we put such a cluster in a simulated Milky Way galaxy. So start over here. So if we have like a Milky Way galaxy now viewed in projection, so that like the disk is kind of going perpendicular here, we would be here, the sun, and here would be a cluster of stars. And as it orbits around the galaxy, what happens is that the tidal forces start pulling stars out from the cluster. So you can see these tidal tails of stars emerging from the cluster itself. And this is what I mean when I say a tidal stream or a stellar stream of stars. So here's really what is happening to a stellar system as it's orbiting the Milky Way galaxy. And the interesting thing is that then this exact shape of this tidal tail depends on what caused the tidal force, and that is really the distribution of matter in the galaxy.
Can you show it again?
Yeah. I can.
And remind people of the time.
Oh, yeah. There is a time. So this is Okay, so in astronomical time, this is, maybe one orbital time or two. Seems like very short. Yeah, it takes a while. So, yeah, I guess needless to say, we do not see this happening in real time. That's why I'm not showing you the data, but a simulation. So we see a snapshot at the end of how this looks like, and it was like, oh, what could have happened? So, yeah. In this case, it was 800 million years that took to create this stellar stream. And so, okay, so this is our theoretical expectation. Then you might ask, like, well, do we actually see that? Because in Pleiades, we see them as a clump, not as this giant stream. And so it turns out that clusters of stars typically have a slightly different color than any other stars that are generally in the Milky Way. So if you look into the Pleiades, you might notice that they are slightly bluer than other stars surrounding it. And for the Pleiades, that's because they're very young. But for some other clusters, it's just because they're very old. So it kind of works out that you can select stars that have similar colors to stars in a cluster to go search for these tidal tails. And this is something I did with this big survey when I measured colors of hundreds of thousands of stars around this region of a Palomar 5 globular cluster. And here is kind of what I came up with. So if I select stars that have similar colors to the ones that we see in the cluster, we see and create a density map. You see that there is this giant tail on one side, and then also on the other side from the globular cluster. So this is. Yeah, maybe I should say this is okay. Yes, I remember from Lars. Yeah, how to make you appreciate how big this is. So the moon would be is half a degree. So here is the sky projection in degrees. So moon would be something like this. So this is huge on the sky, and it really took us a long time. So features like this have been known for maybe 20 years. Because it's just, you have to have many images of the sky over this huge area and go observe very, very faint stars. So if you can kind of see, so one kind of image that I took was this hexagon field. And we stayed on that for half an hour. So when you have a camera, instead of just clicking, you observe for half an hour, collecting all of the light that you can to produce a map that looks something like this. And so it's been really hard, but we are now at a point that it is very exciting that we are detecting such structures, these stellar streams, and then, well, I think they're just beautiful to look at. But it turns out they're also very useful as a tracer of dark matter, which is the topic of this talk. And to see why, I'll now again go back to models of streams. So here is a model of a stream that was created in a smooth galaxy. So coming here, you probably already know the physicists love spherical cows. So here's my view of the galaxy in this case. Just like a very smooth blob, nothing in it. You get a stream that looks like this. So there are some kinks going around, but for the most part, it's almost a one-dimensional kind of a string of stars in the sky. However, if you make another cartoon picture of the galaxy that is slightly less spherical cow, but still fairly idealized. So now this is my model of dark matter halo with those small clumps. And when I create a model of a stream in that sort of environment, I get something like this. So these are streams that were created on the same orbit. So the original cluster of stars was going in the same direction. It's just that in this case, there's just a lot of other things going on, a lot of those subhalos passing through. And so what they did was disrupt the stream. So there are like stars that are kicked out of the stream over here. There are disruptions. There's like a gap over here. There's just a lot more going on. And our hope with the studies of stellar streams is that we can actually measure how many of those clumps there are in the Milky Way galaxy, and through that learn something about the nature of dark matter. Because we know that from the abundance of those subhalos, we can learn if the dark matter particle is very massive, somewhat massive, or very low mass. And okay, so that's our game plan over here. Now let's look at where the status of the field was before April last year, when everything changed. So here is a map of the sky as viewed from the SDSS survey. So this was like another huge a survey of really all of the sky that can be seen from New Mexico, like almost all of it. And so the map is showing stars that are most likely to be members of those disrupted clusters, so kind of bluish stars. And you see that there's just a lot of structure over here. If you're like good at memory games, you might recognize this feature over here is what I showed you before on a previous slide. So this is the Palomar 5 cluster, and these are the tails that are coming out. And so you can see that what I was showing before was just one of the many features that are in our own galaxy. So some are much wider. So we know that this is a disrupting dwarf galaxy called Sagittarius, and it's wrapping. You can see throughout all of this picture, and actually going more than 360 degrees around the Milky Way. So this is the biggest structure there is in the stellar halo. But there are also smaller ones. Here's one called the orphan stream. That means, I guess astronomers are not very creative in naming things. Turned out that we couldn't find the parent of this stream. I showed it. They form from a disrupting cluster or dwarf galaxy. Well, there was nothing along this stream, so it was called orphan. And then it turned out that there's many such structures in the galaxy. One that I'll most be focusing on is this very, very thin, hope you can all see it, tidal stream that is called GD1, and it was discovered in 2006. So it is something that has already been known, and it is our prime target for looking for dark matter at this moment, because it's much longer than any other stream that we see, and it is also very narrow. So we think that the perturbations to this kind of string of stars should be more noticeable than in some other stream, like something big like this Sagittarius stream. And this is a great picture to kind of show the status of the field until really very recently. So we had all of those targets, and we kind of had the idea of what we wanted to do. So we wanted to see, as we go along the stream, do we see any signs of perturbation? Like, do we see a gap somewhere, or maybe some stars outside of it? But you can see immediately looking at this that this would be hard, because there's also a lot of the contamination from these fluctuations happening in the background fields as well. So we just didn't really have data that was good enough to really tell anything very concrete about dark matter.
Anna, before you give the next step, let's see if there's any questions.
Yeah. Okay.
So you can basically identify the offspring to the parent by similar color.
Yes.
Age, meaning as well as distance.
Yes.
Okay.
Yes.
The two methods that I
yes.
assume.
Yes, that's assuming, basically. So in this map, color sort of corresponds to distance. So you can see that there is some distance variation along this giant feature, but for the other ones, they look roughly at the same.
You can tell they're in the neighborhood.
Yeah, exactly.
Thank you.
10,000 light years apart.
Yes, that's like thousands of light years across. It's really.
So are the black bands just no data?
Yeah, the black band. So here is you can see the artifacts of the survey. Yeah, where there's no data. Yeah.
And what exactly is being plotted on the intensity axis?
So yeah, it's an interesting map. So typically, what people do when they make these maps, they take three maps at 3 different distances, and then map them in red, green, and blue channel. I don't know if you have ever tried doing that. That's kind of how you get the color image. But in this case, we teamed up with an artist to help us visualize this map better and kind of tease out all of these, both the big structures and the small structures. And what she realized is that this works out better if we, instead of doing the RGB decomposition, we do the HSV, the hue, saturation, and value. So that's why there's no one-to-one mapping between color and distance, but it is all the kind of encoded in this map.
It looks like there's a bit of a kink of the tidal stream as it goes through the globular cluster. Is that real?
Oh, you mean this one?
Yes.
Yes, that is real. That is the basic prediction of. I feel like I should use chalk at a chalk talk, so I'll take this opportunity. So there is something called the tidal radius. So if we have a cluster of stars over here, and let's say center of the galaxy over here, then it turns out that there's like this thing called tidal radius. Which is the radius from which the stars escape. But it's not like they escape from anywhere around us. They escape from 2 points. One that is pointing directly towards the galactic center, and one that is pointing away from it. And so what you're seeing in the kink, so the stars leave. Oh, I will need more drawing space. Oh, that's mine. So what happens is stars that leave, they look something like this. And so what you're seeing over there, the kink, is actually this. And so it's like a beautiful physics problem that you can directly see in the data. Yeah.
Thank you.
Oh, not sure, yeah. Any other questions? Okay. Oh, yeah.
Yeah, you mentioned the 2 populations of blue stars. One are light, young, heavy, bright blue stars.
Yeah.
Hot. The other ones are white dwarfs.
No, it actually turns out that those are blue because they don't have very many contaminations. So they have very few elements heavier than hydrogen and helium. And it turns out that those stars that are typically much older and were formed earlier in the universe, where there's really mostly only hydrogen and helium, that those are bluer because there's not much other chemical elements in the atmospheres of those stars to absorb the light. So that's why they are bluer.
There's a term that's used like in globular clusters called metallicity.
Yes.
That's what you're talking about.
Yes, I'm talking about metallicity. Yeah. So those would be lower metallicity stars that are typically bluer. Yeah. Okay. I will have a diagram like in a couple of slides to show exactly what I mean there. But okay. If there are no other questions, then I can let you know why I'm really excited about doing this sort of experiment at the moment. So as you were saying, so far we only were able to do this with colors, select stars from these progenitors based on their colors. And here is the all-sky map from the Gaia mission. This is the mission that the European Space Agency sent in 2014, I think it was the launch, and that reached. not sure how far away. Anyway, it's in a distant orbit from the Earth. It's not very nearby. We can even if there was a space shuttle, we couldn't send it to this spacecraft. And it's been observing the sky ever since and measuring very precisely not just the colors and brightness of stars, but also their motions. And why this is really important for the study that I am doing is that instead of just selecting stars based on how their colors, we can see that stars that are born together actually move together. So here I'll play the movie kind of forward in time based on the measurements of this mission. You can kind of see all of those kind of small groups of stars moving together. And this movie was made for the 6 million stars that are closest to the sun. So where we have a full velocity vector, and we can kind of see how the stars, if we fast forward the time in the universe, how the stars would be moving. And what we can then do is then revisit the structures that we knew already are present in the Milky Way and try to clean up our sample by selecting only stars that are moving together.
You have to show it again.
Yeah?
And what was the time scale again?
I think this is something like 6 million years in the future.
Okay.
Yeah, so the way this works, we don't see stars, if you go out, you don't see this happening. Oh, maybe I should just point a few things over here. Okay, so these are the Magellanic Clouds. So we don't see them here. And these are some of those clusters of stars that I'm interested in looking if they have trails of stars around them. And so none of those very distant things move. So we can, because the Large Magellanic Cloud and Small Magellanic Cloud, they move very slowly. But some of the more nearby structures move, fast for the astronomical terms. I say this is still 6 million years in the future where you can kind of see them pass by.
6 million years.
So, the way it works is that we can make such movies for the most nearby stars. But the ones that I'm interested in would be farther out, farther from us, something like 10 or 30,000 light years from us. And the reason for that is because we want to see what they tell us about dark matter. And close to the sun, there is dark matter, but there's also a lot of stars. So the effects of dark matter will be kind of washed in. So that's why we want to kind of move out, but it means that we don't really have this data this good, so it'll be not in a movie form, what you'll see next. So what we actually did, what Lars mentioned, on the day, so this was a big thing on April 25th last year. There was a press conference from ESA, the European Space Agency, when they released the data. And this Flatiron Institute in New York, they organized kind of data welcoming party. So they're just a bunch of scientists it kind of came very informally. It was just people said, "Oh, I want to come." So okay, you can come for 3 days to download that data and see what's in it. And the very morning, and the press release was at 11 a.m. European time. So on the East Coast, it was 5 a.m. So it was kind of brutal getting up, but the data was so exciting. And so this is the plot that I made with Adrian Presswell that very same day. So what we did was look into this region of a known stream, the thin, long one called GD1, and then just selected stars that this mission told us should be far away. And so when we did that, so here's the two coordinates on the sky. And those were rotated in such a system that the stream should appear in the middle. And you can see that really just selecting distant stars, we don't see anything yet. We see that there's more stars in this end, but this is just because this is getting closer to the stellar disk of the Milky Way. However, when we look into the motions of the stars, so these coordinates are the velocities or angular velocities of stars along those two axes, along the x-axis and then perpendicular. And so now you see here there are three things. And it turns out that these are the stars in the Milky Way disk, these are the stars in the halo, and then there's like this suspect little thing over here. And you're like, okay, this looks interesting. What happens if we only show the positions of stars, of distant stars, that are moving in this way, like that are in this part of the diagram? So when we do that, we got a map. And it was already like a best view of this stellar stream that we have ever had. And just to make you appreciate, I made the figure I showed you before. It took me like a year to make that figure. This was done in the morning of the data release. So it was something, we are not even familiar with how this works. But this giant crew of people created such a clean data set that was so good and had this new kind of data, not just the colors, but also the motions of the stars that you could immediately see. And what I'm plotting here is not the density, like in any average way. So these are actual positions, like every point here is a star. So you can actually say, like, this one over here is definitely a member of the stream. And this is without the colors, but as you saw in the previous, in the movie, we still have the color information. And so here is the color space or the color magnitude space that astronomers like to look at. And this will get to your question. So here we have on the y-axis is the brightness of a star, with a brighter being on top and smaller number. Never mind that. And on the x-axis, there's a color. And in this, it's a numerical value, but blue is a smaller number, and so on the left, and red is on the right. And so you can see that there is this kind of ridge over here. And what Lars and his group do a lot is understanding the physics of this particular location in this diagram. What we care for this purpose is just that it is sort of separate from everything else over here. So it is blur in that sense. So we can further remove all of those stars that we don't think will be associated by just selecting that kind of dense ridge. And so here is our final selection that includes both the motions of the stars and this blue color cut. And we're so excited when we saw that. It's not, I haven't shown you like before and after figures, but it turns out that with this much cleaner view of the stream, that there are only a handful of contaminating Milky Way stars, that we actually extended the stream length for more than 20 degrees. So that would be like 40 moons on the sky was the length of the stream that was increased with just this really few days of work with this beautiful data set. But what we got really excited about was that now it looks like these are actual gaps. So you can see that there's more stars. There's just higher density here than either here or here. So we thought that these are actually the first time we can for sure say we see something in the stream that might be a perturbation. And they're also different. This gap looks like it's completely empty. So the number of stars here, it looks like it's the same density as below and above the streams. So you think this may be a location where the progenitor, like the parent body of the cluster, completely disrupted, and it's just no longer with us, and then now these two sides of the stream are just kind of drifting apart. But then this one looks like there are still some stars left. And if you look very closely, you might be able to convince yourself that there is sort of like slight overdensity of stars over here. And this reminded us of this expectation that as such structures move through the galaxy, that some stars, when they are encounter a clump of dark matter, can be pulled out of this kind of narrow track in the sky. So we found actually, when you statistically calculate whether this is consistent with the kind of background density, you see that it is not. So this is actually a significant overdensity of stars that have the color of the rest of the stars and also move the same as other stars. And so we found this one that is long and thin, which we call the spur, and this one more diffuse, which we call the blob. And so I feel like the rest of the talk will be sort of a whodunit. So we want to understand what happened to this stream. Can we really tie it back to dark matter? And our best guess at what happened, I'll now first play a movie, starting with like a smooth stream orbiting in a galaxy on its merry way. See something happen. Now that someone is out of picture, but it left a mark. We can see that there is now at the present, when we observe this model as if it were on the Earth and compare it to the data, it looks remarkably similar. So should I play it again? Yeah? Okay. Should we pause a little? Okay, let's just play it again. So, yeah. What we think happened is that there is a loop of stars kind of connecting those two sides of the gap. And when the way we observe them at the present is such that the loop is kind of in projection over here, like this size kind of goes behind and then in front and then connects back to the rest of the stream. And this kind of looks like the data that we observe. So we, with specific timing of this encounter and the properties of the perturber, I was able to map both the length of this spur and also its offset from the stream to kind of match what we see in the data. And so now the question is, since we have this picture of some orange thing that came close to the stream that can do this, is who might have done it? So this is a question for you. Just to have an educated guess. So here is where the stream is in the galaxy. So this is distance from the galactic center on the x-axis, and then height above the stellar disk on the y-axis. And most of the stars in the Milky Way are over here, and here is the sun. And the dark blue is where this stellar stream is at the present, and the light blue is where it's past orbit for the last 5 billion years. So here's kind of where that is with respect to us and other stars in the galaxy. So, okay, I guess the easy one what we started.
Did you say 5 million or 5 billion?
5 billion. Yes. It's it takes a while to move around the galaxy. Yes. And so, okay, the obvious one, or the one that we started with, was wondering whether this could have been a dark matter halo or a clump of dark matter. But any other ideas? What do you think could have done it?
Magellanic Cloud.
Magellanic Cloud. Good. Anyone else? I will expand this to mean not just the Magellanic Cloud, but there are other satellites of the Milky Way as well. So there's something like 150 globular clusters and something like 60 smaller dwarf galaxies are also orbiting. So that might be one class of object that could have done it. Anything else?
The solar system.
The solar system. Let's just think about it in a way. I guess the solar system, yeah, it's a good. So the sun is, well, if our orbit is correct, it looks like this never came very, very close to the sun. So the closest it came would be like something like 50,000 or anyway on the order of 10,000 light years away. So the actual solar system might not have done it, but
How about a supermassive black hole?
very good. Yes, that's a plausible thing. It is dark. It is massive. It's something we should look at, and we'll come to it. What I won't come to is whether it could be something else, maybe some other sort of system in the stellar disk, because we think that there's just not that much matter in the location where this did cross the disk. But it is anyway. It's a good point. Yes.
Any nearby white dwarfs or neutron stars?
Good. So those are also interesting candidates to check.
Quasars.
Because what?
Quasars.
Oh, quasars? No. So, quasars are very far away.
Yeah, they are.
But white dwarfs and neutron stars are faint, so maybe we would not be able to detect them. And they could do it. And it's interesting suggestion in the sense that we could, like the supermassive black hole, they're both dark, but they have very different masses. So this is like a great segue to, and I think we got it covered, everything that I wanted to to mention. So we have other satellites on the Milky Way, dark matter clumps, and a black hole. And to kind of distinguish between those, we need to talk about how done it. So the difference between the neutron star and the black hole would be the mass. So it looks like if we can estimate the mass of this object, we might say whether it is something more like a black hole or a supermassive black hole or a neutron star. What else do you think would be an interesting measure of that could provide us some clues on whether anything of the to kind of narrow down what happened here? Yeah?
I'm curious, when you watch that procedure, it heals itself. It gets that problem and it random, and then it heals itself except for that little wisp. Okay, so that would seem to me that it would be small, the perturber.
Very
so
good.
It's hard for a globular cluster to be small.
Yeah, so that's a very good point. We would want to measure the size of it, because then as you say, the black hole is much smaller than a globular cluster, and globular cluster is much smaller than the dark matter clump typically. So measuring the size would be also important, and measuring the mass, as I said. And
would the velocity at which this unknown body crosses the stream have any bearing or any significant bearing that might need to be considered?
It would, indeed. And the reason is because if this object is moving slowly, then it has kind of more time to affect stars in the stream. And if it just passes by, then almost nothing happens, or just very few stars are affected. So velocity would be something that we would be interested in measuring. Yeah?
What would cause dark matter to clump?
Yes, so that's kind of a equilibrium solution from the early universe. It turns out that from this initially the universe was very, very smooth. There were just very slight perturbations, and it's really only through gravity. So there is a fairly uniform kind of distribution of dark matter. There's just tiny nugget that was slightly has a higher density, and then what it then did, it started attracting other matter and kind of growing up, and that's how these early clumps were forming, and then attracting more things close to themselves, and so that's this picture of hierarchical growth of structures in this dark matter universe. And then some of those, if the dark matter particle is light, then that means that typically a particle can have higher speed because it has less mass. And so it's easier for a particle to kind of get out of that clump that is trying to attract it. But if it's massive and can only move slowly, then it kind of gets trapped in those clumps. So that's the picture we have very intuitive picture of why there should be clumps of dark matter and why there should be more of them when the particles of dark matter are heavier. Yeah. Anyone else? I think we actually have all of the things, and even more. Then I had to, for time purposes, limit this to only 3 things that we will consider. So we'll look at the mass, the size of the perturber, and how close it came to the stream. So this will also turn out to be important. In my research paper, I actually did have a velocity here, but when I was talking to Lars, he said, like, oh, maybe instead of these 5 things, maybe we should just narrow down to the 3 most important. And so that's why there's no velocity here, but it is a very important parameter as well. And so the way I explore this, what is the role of all of these 3 parameters, is to kind of look at how a single line would be distorted when we change 1 parameter at a time. So I will build this slide by going in columns, where I will fix everything to all of the parameters, so including velocity, including the time of the impact, the size of the perturber, and its distance from the stream. And change just the mass of the perturber. And always in the central row, I'll show what our fiducial, so what we think is the best solution looks like. And then on top will be a solution where the value is lower, and on bottom the one where the value is higher. And so you can see that in this solution, now this is our line of stars that gets distorted, has this sort of gap, and this spur of stars over here. You can look for two kind of features. We have the size of the gap and kind of the size of the spur. And so you can see if the mass of the perturber is very low, we don't have much of an effect. And if it's kind of high, we have a big effect. And just to immediately go back to that comment of the supermassive black hole, so here's the mass of 5 million solar masses. So this is our fiducial solution. And this is exactly in the range of supermassive black holes. So far, so good. Yeah, this is much more massive than the neutron stars. So we can say, okay, this really needed to be something more massive. And it is in the range of where we do expect dark matter clumps. So we have like these 2 things contending. So let's go. And for the globular clusters, this would be on the massive end. So it would have to be something like the LMC, like the Large Magellanic Cloud. So on like massive satellite of the Milky Way. So okay, let's look at what happens when we change the size of the perturber. So again, our fiducial is here. Here is a black hole solution. So this is basically no size. It's a point mass. It's infinite density. And we can see that there's a huge effect. The gap is large, and the spur is also very big. And here is what we expect for the dark matter subhalo. So those are supposed to be actually fairly fluffy. Even though I keep calling them clumps, they have not that high of a density. And so when we just take this kind of density, or this big perturber with the same mass, we don't get much of an effect, just this small blip. So it looks like if it is dark matter, it will have to be kind of a deviation from what we expect in this naive model of dark matter. And in terms of the globular clusters and dwarf galaxies, this is in the right ballpark. So it looks like it's still a contender. So finally, I'll look into the distance. What difference does distance make? So here is, again, our fiducial case. This is if really the object went right through the stream. And you can see it makes a huge effect. And here is if it kind of passes a fair amount out. So you can see it'll produce this gap, but not really much of a spur. And so we can then limit the minimum distance that this object may come to the stream in order to be a viable contender. And so we'll now go check whether any of the known objects have come close. So one of the many things this Gaia mission has provided us is actually orbits of basically all satellites of the Milky Way galaxy. So we know how all of them move, and we know how this structure that we are interested in has been moving. And so we can calculate the relative distance between this stream and everything else in the galaxy. And all the different color lines are showing different classes of satellites. So the darkest would be the classical, like the most massive satellites, like the Large Magellanic Clouds. And then the lighter ones would be lower mass. And the point is really that nothing came very close. So for any object to be a contender, it would have to come closer than something like 50 parsecs, which would be 150 light years. And this is like what the closest they came would be more than 3,000 light years away. So it looks like we can rule out any of the known luminous objects orbiting the galaxy because they never really came very close to it to actually have done it. And now to distinguish between the black hole and the dark matter, let's look at this mass-size relation. So from the shape of this feature in the sky, we can kind of estimate what the mass and the size should have been. And so they're shown in this gray region of the diagram. And our expectations of where dark matter subhalos should be that we expect from a simulation are in this purple band. And you can see that there's not much overlap. So it would have to be a very curious form of dark matter. And of course, there are theories for very dense types of dark matter that clump more densely. But in this vanilla stage, it would be kind of hard to argue for dark matter. On the other hand, this does allow the black hole. But then the question is, how many black holes should be orbiting like in the Milky Way? And typically the answer is one, and it should be sitting right at the center of the galaxy. So then the question is, why, like really, what happened? Still a question. Are we like seeing a runaway black hole, or is this some interesting, new, unexpected kind of dark matter? And so the real benefit of looking for dark matter in the Milky Way is that we have all these other opportunities. So if we think something happened, something perturbed the stream, and if we can look into this in some other way, maybe we'll learn something more. And so here are just some number of things that we might, if we know the current location of the object, you can point our telescope there, what kind of questions could we ask? So we can say like, okay, well, so far when we thought that we are looking for these gamma rays from dark matter clumps, we didn't know where to look. So we were just kind of averaging over the sky. But now if we focus on one region, we might actually find some signal. So that's shown on the left. If this is such a massive object, it should have produced other perturbations in the galaxy. So if we know kind of where it passed, we might look for those signatures, for example, in the stellar disk, or even in just individual stars moving in the halo, there might be some anomalies close to this perturber at the present. And this is like a great idea. It's hard because currently we don't know. You saw in the movie that the thing went by and on its way somewhere who knows where. And so what we would like to know is to determine the orbit of the perturber to say where it is now. However, with the current data, with just the positions, we really can't do that. And so here I'm showing the 3 different solutions that work fairly well. So here's my model is of a stream that is perturbed and has this loop of stars. And it looks qualitatively similar. So there is a gap, there is a spur on one side, and this is kind of folded behind the stream. And the problem is that these happened at different kind of encounter angles between the different scenarios. And they all produce basically the same signature that we can observe just in the sky when we look at positions only. But it turns out that those three have very different signatures in relative velocities. So this is shown on this right-hand side, that in one case we would expect stars in the spur to be moving at a larger velocity than the stars in the stream, in one to be at a lower, and in one to be kind of moving at exactly the same velocity. And so then the hope was, after just to give you a sense of a timeline, so we made this first discovery like in a week. Then it took 6 months to develop a model that fits, to just understand what's happening. And then we're like, okay, we have this prediction. Now let's go try and measure this, because these I think this conversion works almost exactly. So kilometer a second, let's assume that this is something like mile a second. And this is something we can measure very precisely with the current instrumentation on telescopes. So in the past few weeks, I used a telescope in Arizona, close to Tucson, to measure velocities of stars that are in this region of the stream and also along the spur, and with the hope that we can distinguish these scenarios. And so here is like a very, very preliminary data that I only, a figure that I created yesterday. So you're really seeing this as it happens. So the black points on top are all of the stars that we think are likely members of this stream that we identified back in the day, in like last year. And then the blue ones are the ones we targeted. And so you can see, so this is a very zoomed in fraction. So that gap would be over here, and the spur, you can see it above. And so the dark blue will be stars in the spur, and the light blue are stars in this mainstream. And the new thing that we got was the velocity of those stars, and this is shown in the bottom panel. As you can see, that the stream, like in the dark blue, it kind of has this line. It's everything aligned together, and it looks like the dark points, the ones in the spur, are exactly on top of this line. So it looks like what we are finding is that this solution with no relative velocity looks promising. Yeah?
But the previous slide, if any of those were rotated through 90 degrees, you might have a completely different path, correct?
Yeah.
So.
You mean rotated in? Oh, yeah. So it's moving. Yeah. Yes. Yeah. So I guess I'm doing this minus 80. Yeah. So these are just a few examples out of that whole bunch that fit, and I chose these to show that you can get all sorts of kind of combinations, or like both no signal, like negative signal, and positive signal from the velocities. So what this new data is telling us is we'll be able to rule out some of the models. So we can say it's not this, because, so here we would expect something like 2 kilometers a second difference, and here you just you don't see that. It's like going straight through that. But there is a lot of the other angles that might be possible, and this is something, so I'll be staying here for a couple of more weeks, and I'm hoping to actually calculate what is now this constrained space. So instead of just, what will likely happen, instead of me saying, oh, it's like there, you should, point your telescope there, it'll likely be more like, well, there's this path where it could be. So it's.
Can you give us a phone call?
I can give an update. Yes, I'm hoping to. But that's the where we are going next with this. And just to leave us on the kind of bright note for the future, like one other thing that distinguishes the dark matter and the supermassive black hole solution is that really only if there are two black holes, so one in the center and one like that did this, those are like very different. So if there's only one black hole, then really wouldn't have interacted with any other objects in the galaxy. But with dark matter clumps, we think there should be many. And the hope is that instead of just looking at one stream, we now understand we can do it. We have the sensitivity to do it with many streams in the sky. And so here is just how we think in the coming years the data will become better. So the reason we could do it for this one stream is that the data got better. And we're hoping as data gets better for more streams, we'll actually be able to do that on this, like for not one, but hundreds of streams. So I'll stop here and get more of your questions.
Okay, great. More questions?
I have one. Oh, excuse me. Go ahead.
Start.
In the stream you studied, it looked like you were assuming that pattern resulted from just one collision. Is it possible there were other scenarios?
Yeah, that is interesting. So there's nothing obvious that it's not very, very, very contrived. Mm-hmm. So you could think that maybe something in the way the cluster is disrupting, but this is that physics. So the reason these thin streams are very nice is that we understand how they are disrupting very well. So we see the globular clusters in the Milky Way, and they look very simple. You could imagine if there was like maybe some clump inside a cluster that maybe they could kind of offshoot in a different way, but we don't see that at the present day. So yeah.
I have a question, not really about stellar streams, but is there a difference between the comparison of visible matter and dark matter depending on the size of a galaxy?
Yep. Yes, it turns out that the galaxy like the Milky Way is the most efficient in creating stars. So if you imagine that every galaxy is allotted some fraction of ordinary matter, galaxies like the Milky Way produce most of the stars. And so that means that the fraction of dark matter is higher in galaxies that are both more massive than the Milky Way and also less massive than the Milky Way. So there are a lot of studies trying to understand exactly this fraction of dark matter in low mass galaxies, because they're closer to us, so we can observe them better and see since they're more dark matter dominated, if we can distinguish different models of dark matter by studying this individual object. And so all of those different scenarios that I shown predict different kind of distribution of dark matter even in those dwarf galaxies. So this is one line of research that people are pursuing.
Oh, it is.
Yeah.
But you're not doing it.
I'm not doing it myself now.
Yes, I was wondering, is there any reason you can't have a black hole made out of dark matter?
Yeah, that has been. So yeah, those are called the primordial black holes, or would be like something that collapsed in the early universe. And there are some limits on what to expect, because if those were very common, they would be kind of disrupting other things in the universe. So we would kind of notice that lack of, or that a large fraction of that matter is in those primordial black holes. But that being said, it's very uncertain at the moment. So I think there still might be room that this is a primordial black hole. So and this would kind of alleviated issue for this this black hole not being at the center of the galaxy. But we wouldn't expect many of them. Even if like one exists, it would be like one. So by looking at other streams, and we should be able to tell if it really is just this one that we saw that is looking perturbed, or if many are perturbed. So yeah, if we see signatures in many streams, that I think would argue against those. Yeah.
All right, well, let's thank Anna one more time.